Okay, so we're going to have a think about a phenomenon called refraction. This is another characteristic property of waves, and to illustrate it, I'm going to start off by asking you to think about some water waves which are travelling towards, let's say, the beach. Got the beach down here, and I'm doing a top-down view. So these lines here represent the crests of the waves, the tops of the waves. They're travelling towards the beach down there. Now, as you may or may not know, as water waves travel towards the shore, the beach underneath means that the water tends to get shallower. Fairly obvious. As we go from deeper water further out, we get near the beach, we get shallow water, and that has an effect on the waves. They actually travel slower in shallow water. Wave speed is dependent on the depth of the water, and so far out at sea they'll be travelling quicker. As they get closer to the shore, the wave speed decreases, and that in fact is why waves tend to break. They eventually get to the point where they're going so slowly that they sort of topple over, and we get them breaking near the shore. So the wave speed is getting smaller as they go from deep to shallow water. They're slowing down as they get closer. As we go from the deep to the shallow water, the wave speed is decreasing. Now you may remember, if you've looked at the video on wave speed, the wave speed, the velocity or the speed of a wave, is determined by multiplying frequency and wavelength. Wave speed is frequency times wavelength. So imagine if we've got somebody bobbing up and down here in the water as these waves go by. You can sort of see that the frequency of the waves isn't going to change as they get closer to the shore, because if he's bobbing up and down here, let's say 3 waves come in per second, the waves are going to go past him, so 3 waves will go out per second. So there's no change in frequency, 3 coming in, 3 going out. But if the speed is decreasing, there must therefore be a change in the other variable in that equation. There must be a change in the wavelength. In order for the velocity to get less, the wavelength has to get less. So actually what happens to the waves as they get close to the shore is that they start to bunch up. So I'm going to move him out of the way for the moment. We need to show these waves getting closer together. Okay, the wavelength decreases like that. Okay, so the speed decreases and the wavelength decreases. Alright, so far all we've learned is that as the waves travel slower, they bunch up and we get a smaller wavelength. That doesn't really quite explain this phenomenon of refraction. Refraction means that the waves change direction. Okay, how does this happen? Well, we basically get this when the waves go from, say, deep to shallow water, and I'm going to draw a line across there. I'm going to have, say, my deep water up here, and my shallow water down here. Well, we know what's going to happen as they go from the deep to the shallow. We've just seen they're going to slow down and bunch up a little bit. The wavelength is going to get less. But if I start sending them in from the deep water here to the shallow water, then you'll see that when because I've created a sort of inclined division between the two, so that the part of the wave is going to hit the shallow water first. This part at the bottom here is going to hit the shallow water. These parts up here are still going to keep travelling in the deep water. So they're going to carry on in that direction. But down here, when they hit the shallow water, they start to slow down, and therefore they get to lag behind the other parts of the wave. So what's going to happen down here is that the waves are going to slow down, reduce wavelength, bunch up together, but also we're getting a change of direction. The change of direction has happened because the part of the wave at the bottom has hit the shallow water first, and therefore it's slowed down, and the top part has kept going. One way you could imagine that is if you imagine a car skidding off the road. If the road is quite smooth, the wheels travel quickly on the tarmac. Suppose this is mud or thick grass or something down here, which will slow the wheels down. Then the bottom wheel hits the grass first or the mud first. It slows down. The front wheels are still going, and the car kind of skids round and changes direction. And that's pretty much what's happening with our waves. So if I was drawing now the direction of the waves, I've got them coming in along this direction here, like this. But once they get into the shallow water, they've slowed down, they've swung around a little bit, and they're now heading off more or less in that direction down there. So this is the phenomenon we call refraction, and it means that the waves change direction. If these were now light waves, light rays, travelling, let's say, in air and then moving into something like glass, light slows down when it goes from a less dense to a more dense material. So glass is a lot denser, obviously, than air, so light travels more slowly through the glass, and therefore it slows down, the light rays slow down, and therefore if they're shone in at an angle, they change direction. So we get the phenomenon of refraction with light rays as well. And as we'll see in a subsequent video, we can actually put some numbers onto this and find a little formula which explains the amount by which the direction changes. Just one final point about that. Notice that it all depends on the fact that the light or water waves have hit the barrier at an angle. If they come in straight, then although the wavelengths get bunched up, there's no change in direction. The change in direction has happened because we've got this angle of incidence such that the parts of the wave have hit the barrier first and therefore been slowed down first. So light waves, water waves, when they go from one material to another at an angle, we can get a change in direction, which we call refraction.